Hello viewers. Welcome back to another video of Fun with Math. And in this, we are going to find out area of a circle using Jacobian transformation. So what is Jacobian transformation? It is basically a determinant transformation, which is converting the Cartesian integral to a polar integral, right? The limits will be converted from Cartesian to polar. So what is there in our kitty is we have a circle, right, whose area we are trying to find out, and the circle has a radius capital R. So the circle in contention is having a radius R, correct? Now, I have drawn the circle on XY axis, as you can see. So let us consider a smaller circle inside the bigger circle, which has a radius small r, and consider this point to be P. So consider a point P. As you can see, point P has a coordinates xy, right? And you can say the center of the circle is considered to be origin. So the position vector of point P is r, making an angle theta with the x-axis. So the smaller circle, the orange circle I have drawn, consider a point P on the circumference of that circle. It has a coordinates xy and it has a radius smaller. Clearly, one can see the projection of small r on x-axis is small x, and the projection of small r on the y-axis is small y, right? So one can clearly see that the equation of the smaller circle, it will be equal to x square plus y square equal to r square, where one can easily write by writing the components. That is, so one can say clearly x equal to r cos theta and y is equals to r sin theta. Let me mark this as equation 1 and equation 2. Why we require this is when we do the Jacobian transformation, that is from xy coordinate to theta and r coordinate. The polar coordinates are theta and r. So any area which we are calculating, because what we are finally doing, we are calculating the area of the circle. So any area which we are calculating within the circle, it is a small area which is dx into dy, right? So the small area which is dx times dy equals, so we can write dx dy as Jacobian d theta dr. So what we are doing is we are converting the small area dx and dy, that is dx dy. Dx into dy is that small area. As you can see, I have drawn a little bit a small dr here. So what is this dr? This dr is a small increase in r along the direction of the radius. So that means that this r, small r, is tending to 0 to capital R. So this dr can be resolved into two components, dx and dy. So the area dx dy is Jacobian times d theta dr, right? So this Jacobian J is Jacobian transformation of xy to r theta, correct? So how do we write the Jacobian? It is basically a determinant. So Jacobian, it is equal to the determinant. Now, this is a determinant involving partial derivatives. So this can be written as del x by del r, del x by del theta, del y by del r, and del y by del theta. So the four elements of this determinant is del x by del r, del x by del theta, del y by del r, del y by del theta. Now, when we do partial derivatives, we consider the other variable to be constant. So basically, what we are doing here is, so let me do it here. That is, you see, x is equals to r cos theta. So when we do del x by del r, right, then basically it is del by del r of r cos theta. And then theta is considered to be constant because it is derivative with respect to r only. So cos theta remains and del r by del r becomes 1. Okay, so del x by del r is cos theta. Similarly, del x by del theta. Now, when we are doing the derivative of x with respect to theta, we consider r to be constant. So therefore, your r will remain as it is, and del by del theta of cos theta is minus sine theta. So this will become minus r sine theta. So let us simultaneously start substituting as well. So del x by del r is cos theta, and del x by del theta is minus r sine theta. Let us now evaluate del y by del r. Del y by del r, it will be again only sine theta will be left. Del r by del r is 1, and del y by del theta, it will be r, and del by del theta of sine theta, it will be cos theta. It will be positive r cos theta. So this is sine theta, and this is r cos theta. Now we will evaluate this Jacobian using the same rules of how we solve a normal 2 cross 2 determinant. So it will be like this: cos theta times r cos theta. So it will be r cos square theta minus sine theta times minus r sine theta. So minus minus plus, that is r sine square theta. If we take r common, cos square theta plus sine square theta becomes 1. So the Jacobian comes out to be r only, right? Now I'll do the remaining part on this side. So let me rub this heading. Yeah. So we have found out what is the Jacobian. The Jacobian of transformation from xy to r theta is r, right? That means we can say that dx dy. So I'm rewriting this basically. So my dx dy is equals to Jacobian is r d theta dr, right? Now, so we have found out what is x and y. We have converted that into the polar coordinates r and theta. Now, to cover the entire area of the circle, to cover the entire area of the circle of radius equal to capital R, which is the our main circle, which we are trying to find out the area for. The limits would be, so the area A, it will be double integral dx dy But now dx and dy is r d theta dr. So it will be integral d theta 0 to 2 pi. The entire circle will be covered if the integral goes from, the theta goes from 0 to 2 pi, covering. And the second integral, which is r dr, right? I have just substituted for dx dy. So r d theta dr, d theta going from 0 to 2 pi, and the other integral r dr going from 0 to r, right? Now the integral is pretty simple. So your r dr is r squared by 2. You put the limits capital R and 0, you get r squared by 2. And now you are left with this d theta 0 to 2 pi. Integral of d theta is theta, and you put the limits 2 pi minus 0, that is 2 pi. So area is r squared by 2 times 2 pi. So this 2 gets cancelled, and you get your final result. Area is pi r square, which is our well-known identity for area of circle, pi r square. Okay, so this is what we have covered in this video. Okay, so I will be coming up with more exciting videos, fun with math, of calculating the areas and volumes of many such symmetrical bodies using calculus, trigonometry, right? Okay, that's all. Thank you so much. Bye bye.